All right, you guys, can you guys hear me? Think you guys can hear me now. So we're going to be reviewing for our final. You guys can ask me questions about any topics, objectives, things like that you guys would like me to explain. So feel free to ask away. Anything that you guys have questions with, sample problems, things like that, more than happy to help out. And it looks like my writing pen might be running out of, okay, battery. So hopefully I won't have too many problems. Hopefully I won't run out of battery. Q equals MC delta P delta T. We've gone over this a lot, but I'll go over it one more time. MC delta T. So when you're thinking about this problem, don't forget that Q represents your heat or your energy, and we will always have it represented in joules or calories. M represents your mass, which will always be in grams. C represents your heat capacity. And that's in joules, grams times degrees Celsius, or it could be in calories over grams times degrees Celsius. So it can be in several different ways. And then this is going to be your change in temperature. This is going to be T final minus T initial. And then this will be in degrees Celsius. Okay. So I have a feeling, you guys, there might be a little bit of a problem. My pen on my board is not charging, so I'm having a little bit of a problem. So I don't know how long this is going to last on here, and really how much we can do. Sorry for the inconvenience. I didn't realize that my pen was not working. Okay, so if we look at this problem, we could think of a couple different example problems. So for example, we might have an example problem that says how much heat is required to raise the temperature of water. And let's say that we have 80 grams of it. Let's say we want to raise the temperature of the water from, let's say, negative 10 degrees Celsius to, say, negative 5 degrees Celsius. So good habit to do is to make sure that you always are isolating or identifying what you're given. So we know that we have 80 grams. We know my T initial, which is negative 10 degrees Celsius. We know my T final, which is negative 5 degrees Celsius. And my heat capacity, which I did not write down, but I will write down right here, is 1.8 joules grams times degrees Celsius. So once we know all of our variables, what we can do is we can plug them into our equation. So we have Q equals our mass times our heat capacity, and then our change in temperature. So final minus 5 degrees Celsius minus a negative 10 degrees Celsius. So notice that negative, which will end up being 5 degrees Celsius. And you can also see that my units will cancel out. And if we plug this into our calculator, and you know what? I did not grab one. You guys give me 1 second while I go grab a calculator. All right, So let's see. Plugging this into my calculator, we get 4.18 times 80 times 5, and we will get this to be 1,672 joules. Now, because this is positive, this means that this process is endothermic, which means that heat is required. If for some reason this was reversed, so say that we were going from 10 to 5 from 5 degrees to 10 degrees Celsius, this would be negative, which means that'd be exothermic. So remember that if Q is, so this is positive, but if Q was negative, our process would be exothermic. So we do have that difference. To talk a little bit about endothermic and exothermic, one of the things that you want to think about is exothermic means that heat's being released. If heat's being released, that means that if you're holding the substance, it might feel hot. However, if you have something like something that's endothermic, what you might feel is that your hands are getting cold if you're holding it because heat's going from your hands into the system because heat's being absorbed. So there's lots of different ways that we can look at endothermic and exothermic, but you definitely want to know the definition and also what phase changes may or may not be endothermic and exothermic. Basic naming ionic and covalent bonds with some examples. So whenever you come across naming, the first thing you want to think about is the compound ionic or covalent. So there is, of course, one way you can always know ionic is between a metal and a nonmetal, where covalent is between a nonmetal and another nonmetal. If you are dealing with an ionic compound, there's a couple different things that you need to be aware of. You do need to pay special attention to charge. So you want to make sure that you are paying attention to the fact that your charges must be balanced. So what do I mean by that? Let's look at a couple different examples. Let's say that you were given the compound sulfur, let's see, not sulfur, excuse me. Confusing myself. Let's say that you're given the compound magnesium fluoride. And let's say that, this should be you. And let's say that you're asked to write the chemical formula for this. We know it's an ionic compound because magnesium is a metal. You can find it on the right side of the periodic table, so you automatically know that it's a metal. But what you want to think about is we want to be able to write this, and we want to be able to say, okay, magnesium has a chemical charge of, atomic symbol of Mg. It's in that second column, so we know that it will form a +2 charge. Do know what columns form what charges. That's really important. Fluoride comes from fluorine, and knowing where it is, we know that it will have a -1 charge. When I mean charges, this is what I'm talking about, is the idea that magnesium has a +2 charge, fluorine has a -1. So these charges must be balanced out. So if we want to balance out these charges, we need to show that we're going to have 2 of these. So we need to show that for every 1 magnesium, we're going to have 2 fluorines, because the charges must add up to equal 0. So if we have a +2 here, we have to have a -2 over here. And the only way to do that is to multiply fluorine by 2. Now, when we write this in a chemical formula, we have magnesium, fluorine, and then we put what's called a subscript of 2 to show that we have 2 fluorines. So you want to be careful with how you're doing that. When you are looking at covalent compounds, they're a little bit easier because you actually don't have to pay attention to charges, but you do have to realize that covalent compounds have prefixes. So say that you have, let me see, I want orange. Actually, I want black. Let's say that we have nitrogen dioxide. Well, if there is no prefix in this first one, that means that we only have one of these, so we only have one nitrogen. We want to look at the prefix here, and we realize that di is a prefix for 2, and oxide comes from oxygen. So what that means is that we have 2 oxygen, and to write that, we go O2. We might have something like, let's see, let's say that we have dihydrogen dioxide. Now, notice that we have now a 2 in front of our hydrogens. So if we were to rewrite that, now we have 2 hydrogens. So we're going to say H2. We have 2 oxygens, so we're going to put O2. So again, notice the difference between naming ionic and covalent bonds. I would say that definitely the most challenging ones to name are going to be your ionic bonds because, again, you have to make sure that your charges are balanced. So double check that and then make sure that your charges are balanced. Alpha and beta decay. All right, let's go ahead and look a little bit over alpha and beta decay. So we've done this, and when we think about alpha decay, our alpha particle looks like this. It looks like a helium atom in a way. It has 2 protons, which we can tell by right here, and it has 2 neutrons. And we know that because this right here is our mass number, and the mass number is number of protons and number of neutrons. Beta decay, on the other hand, looks like, in a way, an ejected electron, but notice that it has a -1 right here. So it actually adds a proton. So let's look at an example of both of these. Let me bring up my periodic table so I can actually do a real example. So give me a minute. All right. So let's say that we were looking at plutonium, let's say 245. And let's say that we wanted to show that this went under alpha decay. So the first thing you want to be able to do is write this into isotopic or isotope notation. So we're going to have Pu, which is for plutonium. Right here is its mass number. And then down here, we're going to be putting the atomic number, which is atomic number 94. And we're going to show that it undergoes alpha decay. And when we do that, we want to show that it releases an alpha particle. So we're going to have H2He. What you want to do is that your mass numbers need to be conserved, and your atomic numbers, or your atomic number down here, also needs to be conserved. So whatever adds up on this side must equal this, and whatever adds up down here must equal that. So if I wanted to figure out what is being produced, what I'm going to be thinking of is 4 plus what is going to equal 245, or 245 minus 4 is going to be 241. So that's going to be my mass number of my new element that's created. And then we're going to have 94 plus or minus 2, which is going to be 92. And if you look at your periodic table, we need to identify what element this is. And of course, you can identify that element by looking at this number right here. So what we see is that that is uranium. And so that is undergoing alpha decay. Now let's say that we take this uranium-192 and let's say that it undergoes beta decay. So now we're going to have uranium, so 241, 92, uranium, and now we're going to show that it undergoes beta decay. So we're going to put a beta particle right here. And again, we still want our tops and our bottoms to be equal. So we still want this to be equal on both sides. So because this is 0 right here, this is not going to change. So it's still 241. But what plus -1 is going to equal 92? The answer is 93. And that gives us neptunium, which is Np. And so there is an alpha and beta decay for both of those. So you definitely do want to know how to write those. And you also want to be able to go in between these two notations. So being able to write this notation and turning it into your isotope notation. All right. Let's do some grams to moles problems. So let's see. Give me a minute, you guys. Just that. Okay. So we have a problem that says how many grams are in 0.56 moles of potassium. And of course, K is the chemical symbol for potassium. Now, one of the things that you want to remember when you're doing this is that if we're converting between grams and moles, the conversion factor that we want to use for this is molar mass, which is what we're going to find on the periodic table. The units for molar mass are however many grams, which you'll see on the periodic table, will always equal 1 mole. So we create kind of this conversion factor with it. So if we look at our periodic table and we look at potassium, what we see, and you know what, I do not have the periodic table that you guys have in front of you. I have one that I'm looking at on my phone, so the masses might be a little bit different. So for me, the mass that I'm looking at for potassium says that potassium has a molar mass of 39.098, and what that means is that it's going to be 39.098 grams equals 1 mole, and that's for potassium. This is going to be our conversion factor to get us to moles. When you set up this problem using dimensional analysis, you want to make sure that you always start with your number of moles. So over here, I'm going to have 0.56 moles. And I'm going to go ahead and plug in my conversion factor, making sure that my units cancel out and the units have to be on opposite sides. So moles cancels out. The rest, or the other half of my equation, is going to go on top. And again, don't forget that you find this. Let me make sure I make a note. Find value on periodic table. Now, when you're doing these problems, you want to remember that you multiply everything on top and you divide by the bottom. Now, luckily, my bottom right here is just 1, so dividing by 1 wouldn't change anything. And then we're going to multiply these across. Let me pull out my calculator again. Calculator, 0.56 times 39.098. And I'm going to cut this off so it's not quite as long, but I'm going to get 21.89. Whoops, that's a weird 9 grams. So this is how many grams it would equal. And again, I cut it off a little bit so that I didn't have all those digits. 2 digits is more than enough after decimal place to show. So definitely remember how to do these conversions and making sure that you are looking at the periodic table to find that value, and you're also plugging it in so that your units cancel out. All right. How are all elements made? Do stars make all the elements? I'm not sure. Okay, so inside of a star, we have a process called fusion. So in stars, there is a process called fusion. Fusion means that we are combining, combining elements together to make larger elements. Sorry, my handwriting's getting a little messy. So what that means is that in stars, when we have a star undergoes fusion to actually release all that energy, And what happens is that we have a bunch of hydrogen inside stars. These two hydrogens fuse together, and when they fuse together, they create helium. Helium might fuse together with a hydrogen atom, and what we would then produce is beryllium, and so on and so on and so on. So if we did this and we fuse it together, we would create something heavier. So notice that fusion, combining all these smaller elements, will create larger elements. So inside a star, to begin with, there's only hydrogen. As stars will continue to fuse these elements together until they get to iron. Really, iron is about the cutoff point where stars will fuse. After that, there's another process that we didn't talk about, and you guys don't need to know, to create other elements. But a lot of our elements, the ones that we see on Earth, the things that we come in contact on a regular basis, are from stars. They were fused in the center of stars. Hydrogen atoms, larger atoms, fused together or combined in a way so that they created larger atoms. So that is why, or that is how, all of our atoms were created. Can you explain the difference between heat and temperature? When we talk about heat and temperature, one of the important things that you want to realize is that heat is a transfer of energy. And in particular, it's a transfer of energy from a warm object to a cold object. So for example, one of the examples I always like to think about is if you had, say, a cup of water and it had some ice in there and it's a warm day. Well, what's going to happen is that heat is going to flow, and remember the chemical symbol for heat is Q. If the outside is warmer, heat is going to flow into your cup or into your cold glass from the warmer outside into the colder glass so it's going to flow until the temperatures are equal. Once the temperatures are equal, we have then created something called, thermal equilibrium. And once the inside and the outside are the same temperatures, we won't have that transfer of energy. Now, this compares to temperature because temperature measures the movement, or the more proper scientific word, the kinetic energy of particles. When things move faster, they have a higher temperature. So one of the ways that we've talked about this was drawing particles. And we drew particles and we drew particle movement with arrows. The longer the arrow, the faster they're moving. So we could talk about, say, particles moving like this and particles moving really slowly. Right here, we have increased kinetic energy or increased movement and an increase in temperature. Where over here, we have decreased kinetic energy or decreased movement and a decrease in temperature. So temperature directly measures how particles are moving, at what speed. Where up here, we're not talking about the speed, we're just talking about how heat is being moved from a warmer object to a cooler object. So that is the difference between our heat and temperature. Okay, so that I think has wrapped us up into this. So if you guys have any more questions, please feel free to ask. Anything that you guys want me to go over. So I'll wait a minute. Any other questions? You guys feel free to ask questions. If you guys don't have any more questions, we'll just call it good. So if you guys do have questions, please feel free to type them into the chat. Finding half-life. All right, let's talk a little bit about half-life. So half-life is how long it takes for half a sample to decay. So let's say, for example, Zoe, you're gonna have to explain how to do it, what you mean by how to do a trend. I'm not sure I understand what you mean, what kind of trend or what you're talking about. So if you can clarify that. Okay, so if we have half-life, let's say that we have a sample of, I don't know, uranium-235. Let's say that we start off with 30 grams of it. After one half-life, we will have half that amount. So we will actually have 15 grams. So every time one half-life passes, we have half the amount of sample. For example, if we have another half-life that passed by, we will have half the original amount again. So we'll have 7.5 grams. And then, of course, if we have another half-life, we can see that we would have half that, 3.5, 2.5, 3.75 grams. So each half-life, we have half of our original sample left. This amount of time that passes, this half-life, is going to be the same each time. You'll have to look this up. I don't know the half-life of uranium-235 off the top of my head. It's in the millions of years or thousands of years, but it's really high. So this would be the same each time. Let's say that we had a problem, however, that said a sample, well, let's say actually not just a sample, backtrack. Let's say a radioactive sample was, let's say, shipped from one location to another. The shipping, this is kind of a weird sounding problem. I haven't thought this through. Took, let's say, 60 hours. Originally, the sample was, let's say, 20 grams. After 60 hours, let's see, 2.5 grams were left. So our question is, what is the half-life? I'm going to need to show my work up here. Okay, so the first thing we want to do is we need to figure out how did we get from 20 to 25. So if I have 20 grams, my first half-life, I would have 10 grams. My second half-life, I would have 5 grams. And my third half-life would be 2.5 grams. So what we see is that 3 half-lives have passed. Now, if we know that the time was 60 hours, we can then figure out that 60 divided by 3, because we know 3 half-lives occurred within 60 hours, equals 20 hours. So what we end up finding out is that the half-life of the substance is 20 hours, because we could backtrack and calculate that. Can you explain ionizing energy and the atomic radius? Okay, so let's talk a little bit about some of the trends that we saw. So let's say that I'm going to kind of draw an outline of the periodic table. You guys, my pen is slowly dying, so I don't know how much longer I have for writing. Okay, so let's say that, oh, this got really messy. That's not what I wanted to do. Oh, well, we'll start over. Okay. Here's my very messy periodic table. Okay, so we could talk about a couple different trends. First, let's talk about atomic radius. Going across a period from left to right, what we see is that the atomic radius actually decreases. And the reason why it decreases as we go across a row is that we have more protons in the center. Those protons in the center are pulling on those outer electrons, and it pulls them in tighter. And if those electrons are being pulled in tighter, that radius gets smaller. As we go down a row, our atomic radius, and I'm just going to put AR, actually increases. And the reason why it increases is because as we go down a row, we have more energy levels. So for instance, here we might have 1, here we have 2, here we'll have 3. And as we can see, if those electrons are being held higher out because they're in higher energy levels, that means that our atomic radius has increased. So how far they are or where those electrons are is important. So here it has to do with the number of protons. Here what it has to do with is how far out those energy levels are. And again, atomic radius increases as we go down and decreases as we go across. We also talked about ionizing energy. And this is the energy required to remove an electron. Energy to remove an electron. If that electron is really close to the nucleus, that means that it has a strong attraction to the nucleus. It's going to be harder to remove. Whereas if it's further away from the nucleus, the attraction to the nucleus is smaller, so it's going to be easier to remove. So if we think about ionization energy and we go from left to right, ionization energy, what we're going to see is that it's going to increase. Because as we go from left to right, that electron is closer to the nucleus, which means that we're going to have a stronger Coulombic attraction, which means that it's going to be harder to remove. Where if we talk about going down, what we see is that it's actually going to, whoops, let me go back. It's going to, whoops, wrong one. Going to decrease, and it's going to decrease because those electrons are further away from the nucleus, so the attraction is not as strong, so they're going to be easier to remove, which means they don't require as much energy. The other one that we have is electronegativity. And electronegativity has to do with how strongly it's going to attract an electron from another element. So when we think about that, if we have, say, an electron over here, and we have, say that this is some element right here, and we have another electron over here, this atom is going to be attracting this electron. And we talked a lot about that idea in class as to why that happens. But the closer that this nucleus is to this electron, the stronger it's going to attract it. So if we think about ionization, or excuse me, electronegativity, it has the same trend as ionization energy. It's going to increase as we go from left to right because that nucleus is going to be closer to that outer electron. And as we go down, my electronegativity is going to decrease because that electron is going to be further out, and the further out it is, the weaker the attraction is going to be. So definitely know those trends. Modern atomic theory, linking experimental evidence. The main thing that you want to know with that is just that when we talk about atomic theory, I'm just going to talk my way through this. There isn't really much to draw. When we talk about atomic theory, you just want to realize that our view of the atom has been a very progressive view. we started with the idea that Democritus said that everything was created of atoms. And then we have John Dalton, and John Dalton said that, okay, well, we have atoms and they're these small solid spheres. Then we figured out that there were these positive regions of an atom, and we had what was called the plum pudding model, which was still a solid sphere, but we had these small positive particles within there. And then we come to Rutherford, and Rutherford said that, like, no, actually, it's not a small solid sphere. It's actually mostly empty space. We have this very, very, very dense nucleus composed of something that's positive, and we have these electrons that orbit the nucleus like planets. And then from there, we got to things like the Bohr's model and what we now know as quantum mechanics. So the idea that our view of the atom is a very progressive view. And as I mentioned in class, I believe is that, you know, I do not believe that what we know about the atom is all there is to know about the atom. I'm sure that as we continue to move on, we'll have even a more clear idea of what the atom looks like. But again, it really has to do with our technology and how powerful our technology is. Ione, those people are part of the atomic theory. So if you feel like you need to put them on your worksheet or on your 3x5 card, you can, but they are part of the modern atomic theory. Can you talk about how colors, hold on. Can you talk about how colors are affected with different elements and how we use that? Okay, so when we talk about colors and what we see with an atom, so if we look at an atom, we have a nucleus and we have these different rings around a nucleus, and these are where our electrons are. So let's say that we have an electron right here. An electron can absorb a certain amount of energy. So let's say that we have some energy and it absorbs it. In the observations or in the experiment that I did or the demo that I did in class, the energy that was absorbed was from a flame. So it provided a certain amount of energy. What happened was that that electron absorbed that energy and it couldn't stay in this ring right here. So what it did is that it got excited and it moved up into a higher energy level. Now it cannot stay in that higher energy level for too long. So what ends up happening is that it relaxes back down. I'm going to move it over here. And when it relaxes back down, it has to emit some of that energy. So some of that energy is going to be emitted. And that energy that it emitted can be viewed as light. So depending on how much energy it emits, it can be emitted as light. Now, depending on what color we see, we can know kind of how far it traveled. So if we think of Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, this one right here is low energy, and this one down here is high energy. So if this electron moved, say, not that far, it might only release a color like red. The further down it moves, the more energy it has to release. So the higher up that energy is going to be. So based off of how far that electron or what kind of light it emits, we can figure out how far that electron relaxed back down to what's called its ground state. You don't need to know that, but the idea that it can move up when it absorbs energy, when it relaxes back down, it's going to release energy, and that energy is usually going to be in the form of visible light. Depending on what color we see, that's going to tell us about how far it actually relaxed back down. So Serena, I hope that kind of answered your question about the colors that we see. All right, any other questions? There could be, and I kind of already reviewed that. So you want to go back to the beginning of the video. I talked a little bit about naming ionic and covalent bonds. I'm not going to say for sure if it's going to be on there or not. You might see that on there. So you definitely want to review that. That was on, I think, unit 4th, I think. So I would go back and review those. But I did talk about that. That was like the second thing I talked about. Other questions? All right. So it seems like that might be the last of it. So I'm going to go ahead and call it good. I hope that you guys are reviewing. Make sure that you definitely create a 3x5 card and make sure you review all your other old tests and quizzes. I'll wait one more minute, but ask a question. All right, I'll answer 2 more questions and then I'm calling it good. So Bohr's diagram is actually this right here. This example that I had right here is Bohr's diagram. When we think about Bohr's diagram, we have our nucleus and we have these different regions. We call these energy levels and they're represented by N. So N equals 1, that can hold 2 electrons. N equals 2 can hold 8 electrons and so on. So if we have something like, let's say, let me bring up my periodic table. Let's say that we have boron, and we know that boron has 5 protons. And if it's neutral, if it has no charge, that also means that it has 5 electrons. So we can put those electrons in here. We want to fill up the first shell. So once we fill up that, which it can only hold 2 electrons, we move on to the next one. And then we could put our last 3 right there. And so that would be a Bohr's diagram, just being able to draw those into each energy level. Our subatomic particles, we have 3. We have a proton, we have a neutron, and we have an electron. These 2 are found in the nucleus. These are found in the surroundings area, so anywhere outside the nucleus. A proton obviously is a +1 charge. Oops. A neutron is 0, and an electron is -1. So +1, 0, -1. We can also talk about their mass, and we talked about their mass according to AMUs, and we said that a proton is about 1 AMU. A neutron is about 1 AMU. And an electron is really small. It's like 1/1800th of an AMU. I mean, it's so small that we usually say it's about 0 because compared to the proton and neutron, it has almost no mass. When we think about this, this makes sense when we've talked about the mass number. We said that the mass number is represented by the number of protons and neutrons, and we call it the mass number because the number of protons and neutrons is really where all the mass is. That also explains why we talk about the nucleus and we said that the nucleus is so dense, is that that's where all the mass is. All the mass is in the nucleus. There's really only the electrons, and electrons make up such a small portion of that. So there really isn't much more there. If we're thinking about this, let's say that we have, hold on. Let's say that we have calcium and it has a 2+ charge. Let's say that I want to figure out the number of protons, neutrons, and electrons. The first thing that I know is that calcium, it has an atomic number of 20. And that tells me that I have 20 protons. So then the atomic number is the number of protons. Let's say that this is also not just calcium, but let's say this is calcium. Let's say this is calcium 41. So that right here that I just wrote down, that's my mass number. So my mass number equals 41. And that tells me the number of protons plus the number of neutrons. Now, if my mass number is 41 and I know I have 20 protons, I can easily figure out how many neutrons I have. What that means is 41 minus 20 is going to equal my number of neutrons, which means that I have 21 neutrons. Now, this positive charge right here has to do with electrons. If it's a positive, that means that I lost electrons. If it's negative, that means I gained electrons. Now, since it's a positive 2, that means I lost 2 electrons. So according to this tells me that I lost 2 electrons. If I lost 2 electrons, if it was neutral, I would have had 20 electrons because the positive and the negative need to equal each other out. So if I had 20 protons to begin with, and if this was neutral, that means I had 20 electrons, but it's not neutral. It says I lost 2 electrons. That then means that I have 18 electrons. So here I have, if we look at this, I have 20 protons, and I get that from the atomic number that you find on the periodic table. I have 21 neutrons, and that's from taking the mass number and subtracting the number of protons. And I have 18 electrons. And that tells me from the charge right here. If there was no charge, again, if there was no charge, the number of protons would equal the number of electrons. But since there is a charge, that tells me that I have 18 electrons. So definitely know about your numbers, know how to read them, know how to calculate them, and things like that. That's definitely an important idea. All right, you guys. So again, make sure you guys have your 3x5 card. Make sure you guys have notes written on your 3x5 card to have for your final. I would definitely make sure that you review your old quizzes and things like that, run through the multiple choice problems that are on there just to give it another once over. I will see you guys if you're in first period. You guys have your final tomorrow, so I will see you guys bright and early tomorrow. Make sure you're not late. School does start at 7:35, so make sure you guys are there on time because we will be starting the final right away. Have a great evening, and I will see you guys tomorrow.